Okay, it's time to get crazy. Let's imagine a very unusual garden path system as follows. It just has two houses, house A and house B, but the garden path system itself is strange. Here's how it goes. People walk down a path, fine. They come to a three-way fork, okay? They come to a three-way fork. Those that choose to go left, go to house A. Those that go right, go to house B. And those that choose to go straight, come to another three-way fork. Those that go left there, go to house A. Those that go right there, go to house B. Those that go straight there, come to another three-way fork. Those that go left there, go to A. Those that go right there, go to B. Those that go straight, come to another three-way fork. And that is going to happen over and 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 over again forever. Whoa, this is an infinite garden path system. So the question is, what fraction of people will end up in each house, in house A and house B? Can we draw it? And the answer is yes. Here goes. Look at this stunning picture that's going to come out before our very eyes. So let me draw a square of people, a big block of people. What do they first do? They split into thirds, where 1/3 goes to A, 1/3 goes to B, the other third keeps going. So they split into thirds, A and B, A and B, and keep going. But let me do something. Let's make this picture visually stunning. Let me color the people that end up in house A blue, and the people that end up in house B yellow. Hope that's clear enough. So that way, blue people end up here. This is house A, and this is house B. Okay. Then, people that went straight haven't done that yet. These middle people, what do? They split into thirds, where 1/3 goes to A, 1/3 goes to B, and 1/3 keeps going. All right, so, lots of markers. So these middle people split into thirds, of which 1/3 goes to A, 1/3 goes to B, and that third keeps going. But what do? They split into thirds, of which 1/3, they split into thirds, let's do that first, split into thirds, of which 1/3 go to house A, 1/3 go to house B, and the other third keep going, but they split into thirds. Oh my goodness, they split into thirds with 1/3 going to A, 1/3 going to B, and the middle third splitting into thirds. Do it again. These split into thirds. Okay, it's getting tight. So 1/3 going there to A, 1/3 going to B, and the rest of them split into thirds. Oh my God, crazy. Blue, yellow, then split into thirds, and thirds, and thirds, and thirds, and thirds, and thirds forever. So now the question is, stare at the picture and see if we can answer the question, what fraction of people end up in each house? And if you look at this picture, you see this beautiful blue spiral going on forever apparently, this beautiful yellow spiral going on forever, and these two spirals are actually identical. So they must be each taking the same amount of area, they must be taking up half the area of the square. Now I know there's a tiny little space in there. If ever we stopped, there'd be a little bit of space there. It's not quite the full half area, but if this truly could go on forever, it would fill up the whole area, in which case I have to say half the people end up in house A, half the people end up in house B. And there's the picture for it. In fact, this is profound, because look what the picture's really saying. We first sent 1/3. This is 1/3 of the picture. 1/3 of the people went to house A. Then we sent these people 1/3 of 1/3. So we sent 1/9 of them to house A. Then we sent these people 1/3 of 1/9, 1/3 of a third of a third, 1/27th of the people to house A. And then we sent these people 1/3 of a third of a third of a third, 1/81th of the people to house A. Then we added this group of people, 1/3 of a third of a third of a third of a third, 1/243th of the people went to house A. And then this group, 1/2 of a third of a third of a third of a third of a third, 1/729th of the people to house A. And we did this forever, and we said that equals half the people. Whoa! We've just established a crazy, crazy infinite sum. A third plus a 9th plus a 27th plus an 81th, add up all the reciprocals, the powers of 3. And if you could do this forever, if you could really truly do it forever, it'll be half the people, add up to 0.5. Wow. From infinite garden paths. So I'll leave off with a puzzle for you. Can we do something similar with, not with the powers of 3, 1/3, how about with powers of a quarter? So that was 2 houses led me to thirds, so I'm going to do 3 houses and see if it leads me to quarters. House A, House B, House C. All right, put my houses a little bit differently this time. People come down to a garden path. They go to a 4-way fork. They either go to A, to B, to C, or they keep going. If they keep going, they come to a 4-way fork. They either go to A, to B, to C, or they keep going. If they keep going, they come to a 4-way fork. Either to house A, to B, to C, or they keep going. If they keep going, they come to a 4-way fork. To A, to B, to C, and they keep on going. And they do this forever. Can you draw me a picture that goes with this particular garden path system? And if you can you then figure out the value of this sum? 1/4 plus 1/4 squared plus 1/4 cubed plus 1/4 to the 4th power, 256, forever, equals what? Equals what? Now, I have a little piece of advice for you. This one's particularly nice because you know I've thought about this myself. I've got a lovely answer in my head, and I bet you'll come up with the answer too. Don't draw a square for this one. Draw an equilateral triangle. Because you do that, you can naturally divide an equilateral triangle into quarters. Here's a nice way to draw it into quarters. And send the A people here, make them A. Send the B people here, I'll do them in pink, B. And send the C people here, I'll do them in yellow, C. And then the rest of the people, A, B, C, these ones get divided up again. Can you draw a very stunning, beautiful picture using equilateral triangle perhaps this time? And establish a sum here? That's so cool. And then of course the natural next question is, okay, we did powers of a third, we did powers of 4th. Can you then draw me a garden path system for the powers of 5? Whoa. For 625, my handwriting's getting scrawly because I'm very excited. Can you actually figure out a picture for that one as well? In fact, there's an infinite amount of play to do with this infinite garden path system. Wild, crazy fun. Just play. I invite you to play.